Imagine a magical box that can produce anything you desire. Ask it for an apple, and an apple appears. Request a pencil, and one is there. Even wish for a unicorn, and voila, a unicorn appears. But here's the twist. The box doesn't choose what to make until you actually open it and take a look. Until that moment, it holds the potential to become anything. It's only when you open the box that it settles on being just one thing: the apple, the pencil, or the unicorn. All these options exist at once inside the box. This idea mirrors how particles behave in quantum mechanics. Before being observed, a particle exists in a state where it can be many things at once. It's the act of observation that forces it into a specific state, a concept known as the Copenhagen interpretation. According to this interpretation, observing a particle is what causes it to assume a definite form. This phenomenon is called wave function collapse. The moment we measure the particle, we interfere with its state, causing it to leave its state of superposition and become one specific version of itself. In our story, opening the magical box and looking inside is like measuring a quantum particle. It transforms potential into reality, making it become one definite thing. Back in ancient Greece, philosophers believed that everything was made of basic elements like air, fire, or water. This was a groundbreaking idea at the time, trying to explain the complexity of nature with just a few fundamental components. About 100 years ago, scientists thought the atom was the smallest unit of matter. But experiments by Max Planck, Albert Einstein, Niels Bohr, and others showed that atoms are made of even tinier particles, which behave in strange ways that classical physics couldn't explain. Today's physics tells us that matter is built from subatomic particles like electrons, quarks, and neutrinos. These are believed to be the fundamental units of all matter, combining in various ways to form everything we see. Yet, the journey doesn't stop there. Quantum theory suggests that the foundation of the universe isn't just particles, but also includes the very structure of space and time. Instead of simply particles moving through space, the universe is a complex interaction of fields and forces that exist within space-time. These quantum fields, as described by quantum field theory, are the true substance of reality, with particles appearing as disturbances or excitations within them. Today, we understand that the most fundamental layer of existence consists of elementary particles governed by quantum laws. This tiny, invisible world is the source of everything we see, touch, and experience. Originates is a realm filled with amazement, and at times can appear bizarre. Let's begin with our current understanding. Visible matter consists of atoms, each containing protons and neutrons at its core. But these protons and neutrons aren't the most fundamental components. The standard model of particle physics, which describes the universe on the tiniest scales, identifies particles that are even smaller. Astonishingly, everything in existence traces its origins back to atoms. An atom is the basic building block of matter that still maintains the characteristics and behaviors found in the larger visible world, including both physical and chemical traits. At its essence, an atom is a quantum object, possessing defined energy levels, properties, and rules of conservation. It is affected by all four fundamental forces known to physics. In fact, much of physics can be observed by studying just a single atom. Here on Earth, about 90 elements occur naturally, each created by cosmic events. Every element features atoms with a nucleus composed of protons, and sometimes neutrons, encircled by electrons equal in number to the protons. Each element has distinct qualities, including texture, color, melting and boiling temperatures, density, electrical conductivity, electronegativity, ionization energy, and more. What's truly fascinating is that a single characteristic defines the type of atom, and therefore all of these traits, the number of protons within its nucleus. In our daily experiences, we rely on certain principles, such as cause and effect. One thing happens and leads to another. Different beginnings bring about different outcomes. But in the quantum world, the basic rules are inherently different. You can't define your initial conditions with perfect accuracy due to an intrinsic uncertainty tied to some system properties. Instead of precise predictions, quantum physics only offers probabilities of various outcomes. When a measurement, observation, or interaction is made with enough accuracy, you'll observe one specific result. But the act of observing, measuring, or interacting itself alters the state of the system. This strange behavior has sparked scientific debates for nearly 100 years. The most unsettling resolution may be not trying to interpret it at all. As paradoxical as that may sound, interpretations might actually be getting in the way of fully grasping quantum reality. Quantum theory, despite its strangeness, provides an incredibly accurate explanation of the microscopic world, atoms and their components. But it also uncovers a deeply unintuitive reality where, for example, a particle can be in a superposition describes a condition where a system can exist in multiple states simultaneously. In 1935, Erwin Schrödinger proposed his well-known thought experiment to demonstrate a result of quantum mechanics. He envisioned a cat placed inside a sealed box with a container of poison. If a radioactive atom decays, it triggers a hammer to break the container, releasing the poison and killing the cat. Since the atom can be in a superposed state of both decayed and undecayed, the cat ends up being both alive and dead at the same time. The outcome is only revealed when the box is opened. This scenario brought quantum strangeness from the atomic scale into the realm of daily experience, challenging scientists to address its implications. Physicists refer to large-scale superpositions like these, involving many atoms or quantum particles, as Schrödinger's cat states. Over the last 10 years, these scenarios have allowed scientists to study how the quantum world shifts into the classical one. They've also shed light on why we don't encounter objects in dual states in everyday life, and whether it's even possible that we ever could. The notion that a hypothetical quantum creature might be simultaneously dead and alive is a cornerstone of quantum oddity. Questions such as how or why quantum physics functions, or whether the mathematical constructs within it symbolize anything real, have numerous proposed answers. But those interpretations often reveal more about our human biases, assumptions, and outlooks than about the actual universe. In reality, there are only a few things we can directly measure, like a particle's position, momentum, cross-section, scattering behavior, or individual quantum states. Asking what's really happening assumes that reality aligns with our instincts when the truth may be completely alien to us. What we consider real is filtered through our senses and limitations, and the universe's rules might be stranger than anything we expect. We often speak of particles as though they occupy specific locations, but in fact, they are spikes of energy, excitations, in deeper quantum fields. For instance, a photon is a ripple in the electromagnetic field. These fields stretch across all of space, meaning traces of photon-like activity are always present. These are known as virtual particles, which emerge briefly and disappear, even when not enough energy exists to create actual particles. Fields are believed to be more fundamental because the mathematical framework collapses without them. Still, a field's quantum nature makes it impossible to directly observe. Observation demands energy, which causes the field to produce a particle. This is why we often describe what we detect as particles. They are what we're actually capable of observing. Nearly every known particle has an associated